Okay, then there's one chapter left from the last lecture. Let's do that quickly. It's probably not really needed because it's about higher order functions, and the next lecture that I'm starting after that is, the whole lecture is about higher order functions, but nevertheless, let's go over the slides quickly. Right. And as I mentioned before, so by definition, a higher order function is a function that takes a function as an argument or as the result. So a function as an argument and a result. And if either of those types is a function type, then we call it a higher order function. And strictly speaking, as I also mentioned before, every curried function in Haskell is by this definition a higher order function. For example, if we look at the elem function that checks whether a given element A of type A is an element of a list of A's, returns a Boolean if it is, or not, then because of how Haskell normally deals with functions with more than one argument in this curried form, strictly speaking, this is a higher order function by definition, because elem is a function from A to functions from list of A to bool. And we can, for example, also partially apply it. So we can apply 3 to this function, and then we get as a result another function that now checks, takes a list and returns a bool, and that will be true if in this list there's a 3 somewhere, and otherwise it will be false. We can briefly try this. We just open a REPL. Okay, I think I'm in the wrong folder. Where were we? 04. Try this again. Okay, so I can ask, so elem should be in scope. Okay, so it's slightly more general. It doesn't just work for lists, it works for arbitrary containers. Okay, and I can ask for the type of elem3, and we see basically what it says on the slides, except on the slides it's specialized to lists, and here we have it for arbitrary containers. Okay, and so I can give that a name if I want, elem3. So the type of f is now this, and now I, for example, can apply f to a list of integers. Let's say 3 is in there, so I get true, but if I remove the 3, then I get false. So by definition, this would be a higher order function because it has a function as its result type. But normally, it is one, but normally we rather talk about higher order functions when the functions are on an argument. So 2 prime examples are the 2 functions we saw on lists, filter and map. So filter takes a function as argument, a predicate, and then filters, given a list, only keeps the elements of the list that satisfy this predicate. So if I can, for example, take the same list here, if I filter by only the even elements, then the only even element in here is 4. If I filter by odd, then I get 1, 3, 5. So this even or odd are again functions. So filter is a higher order function because it takes an argument, another function. And map we also saw. So for example, I could do map times 2. Sorry, let's take this again, this list. So I could take map times 2, which doubles every element in the list. And again, this argument of map here, the first argument of map is a function, the double function, multiplication by 2 function. So those are higher order functions, filter and map. Okay, set that. Okay, so that's higher order functions. And often, like with higher order functions, we can sort of achieve a similar effect to using overloading. So remember the last topic of Monday's lecture was overloading type classes. There is a function in, I think it's in the prelude sort. If you have a list of A's and A is orderable, so you have an order on A's, then you sort the list. So we can try this out. I think it's in scope automatically. No, it's not. I think then I must import it from data.list. Okay, so now it's in scope, so it's not in the prelude. It's in data.list, and I can get it into get access to it in the REPL also by doing this import and then name of a module. So now I can sort. So if I again take this list I had before, this is, I mean, won't do anything because it's already sorted. But if I, for example, put other elements here, so it will take the list and sort it. And it doesn't just work for numbers, it works for everything in audible class. So in particular, characters are audible. So I can, for example, also apply it to a list of strings. Sorry, a list of characters, which is a string. So this is now ordered. Maybe look a bit weird that the H is on top, but if you mean the ordering of characters follows the Unicode ordering, or specifically the ASCII ordering. And in ASCII, the uppercase letters come before the lowercase letters. So the capital H is the smallest one, and then the lowercase letters are sorted alphabetically. Right, but there's also in data.list, there is this sort by. So you instead, I mean, this one, the sort function relies on this class constraint that the elements of A are an instance of odd. But maybe you want to sort a list where the elements are not, I mean, the type of list elements A is not an instance of odd. Or maybe you want to use a different order. So for example, maybe you want to order them descendingly, not ascendingly, the elements. So for that, there's this sort by function, which doesn't have a class constraint. So A is an arbitrary type, but you must explicitly basically give a comparison function. So this tells you how to compare two A's. So for example, if I wanted to sort this list here descendingly, I could use sort by. And now I must say how to sort them. So one way I can do this is I just say it's the usual compare that comes from the odd constraint, but the other way around. So how would that work? So yeah, just have to. So what I mean, compare we saw is from the odd class. So if I, for example, have whatever 3 and 5, then compare 3 and 5 would be LT, less than, because 3 is less than 5. But with this definition here, if I have 3 and 5, because I flip the arguments here, I compare 5 to 3, so the result would be greater than. So basically flip the ordering around, and the result is that now my elements are sorted descendingly. So if I apply this to Haskell, it's exactly the opposite of what I got before. So now the capital H is at the end and the largest lowercase letter is in the beginning. So both have their advantages and disadvantages. So the first one, I have no control over the sort order. It's given by the odd instance here. So it's always, it always produces a list that's sorted ascendingly according to the instance, the odd instance. This is more flexible because I can give arbitrary orderings here, and A doesn't need to be an instance of odd. But on the other hand, it's also, I mean, I have to explicitly give this additional argument. Right, but both are useful. And as it so happens, under the hood, they are actually implemented very similarly. So, I mean, we haven't said, and we also don't really care how Haskell actually does, I mean, implements these class constraints. But actually what happens is at runtime is that basically it uses something like sort by. So at runtime, it will look up the odd instance, and then there will be like a hidden argument to this function, which takes the sort instance. So if I'm sorting ints, a list of ints, then there will be something of this type basically as the hidden argument, which comes from the board class. So actually at runtime, these two functions are very similar. So in that sense, this sort by is more general. Sort only takes the one instance. And just some remarks on performance. So for parametric polymorphism, that was the first part of last lecture, you don't pay any penalty. So you don't have to worry about performance when doing that. If you use overloading, so classes and instances, there's a small penalty because at runtime, basically this extra argument has to be provided to give information about the instance. It is possible in GHC with a special pragma to tell the compiler to make that faster for specific instances. So for example, if you often have to sort list of ints or so, you could instruct the compiler to make a special case for int. And then the sort function would be faster for ints or any other type you choose. And GHT is also a very powerful compiler. So it inlines a lot. So instead of using indirection, to call function definitions, it often inlines the function definitions into the code itself. So often you don't really have to pay an overhead if the compiler might automatically optimize that away. Right. And just as a recap, so that's the last slide of the lecture from Monday. So parametric polymorphism, that's like generics and other languages, allows us to use the same code for many different types. So you write a function on whatever, on pairs, like swapping the components of a pairs, or extracting the first component or the second component. You write that once and for all the code, and then it works for arbitrary pairs of arbitrary component types. And it's completely unrestricted, so the caller that uses your function can choose for which types to use it. And overloading, on the other hand, uses the same name for functions. For example, this operator or the show function to convert something into a string, but can use different implementations for different types. So that is similar to interfaces in other languages. And right, so that's the difference between the two. And so you can use the same name like show for different code. So if you show an int, different code is executed than if you show a Boolean or show a character. And the type checker and the compiler will figure out which to choose and then give you the right implementation. And we also saw that, interfaces exist in other languages as well, but Haskell is actually very powerful. So the argument of the class can actually appear on methods in both the argument and the result type. So we saw, for example, show, the show class. So a class is, and type is showable. We can ignore these others. The main one is the show one. So it's showable if you can convert an A into a string. So in this case, the A is on the left-hand side. It's an argument to the show function. But we also saw, for example, the read function. So if a type is readable, so you can pass a string into a value of type A, then we see it's a result. And often other languages are not that flexible. So in principle, the A can appear everywhere in the methods, in the signatures of the methods. Right. Okay, I think that's basically that. Are there any questions to this? So now, if not, then let me just close this. So now there would be a whole lecture on higher order functions. However, my colleague suggested that before we start with this, we maybe should do some of the homework things together, just as for some practice. or sorry, Robertino or Karina, which one would you recommend? I mean, the assignment 2 or 1 or?
Yeah, the assignment 2, maybe the data types one, because we have data types and tables, but we already did tables.
Okay. Maybe not the whole thing, but at least let's see.
Yes, just
Maybe
a
I can
few.
start. Yes. So the A2, right? You said.
Yeah.
So maybe I can just, because people sometimes got confused how to do this. Okay, so I'm at our repo again. And so I see this assignment 2. I click on it. Maybe just for fun. Okay, I haven't even accepted it yet, so I need to accept the assignment.
Will be extra harsh on you.
But I already ran. No, I still have time. Okay. Okay.
Maybe you can reload the page.
Yeah, sure. So I think this doesn't work for me, so I click on the link here. And now I have my Taylor, I mean, with my name, the assignment repo. And now I could clone it, or I could also decide to work in the browser.
In the
Not
browser,
sure.
is on top. You have in green.
Oh yeah,
In green.
that one. Yes, right. Yeah, sorry. So I could do that. But then it probably now takes a couple of minutes the first time to prepare everything.
Yes. It has to actually like set up the Docker container.
Yes. Okay, so this. Okay, so it's opening the workspace now. So this probably takes a while. So maybe in the meantime I can, or maybe something is cached there. I mean, that looks actually quite fast. It looks as if all the layers are cached.
Yes, I mean, not sure if those are Ubuntu's layers or others.
It would be nice if it could share between assignments, because a lot of the image is the same between assignments, but I don't know how smart Gitbot is, whether it like has an internal cache for stuff like that.
Yeah.
But
Actually, the image should be the same for all Haskell. And like for Haskell should be the same, and for Bluetooth should be the same. So if it can do that, it should be instantaneous.
But I think it doesn't. It tries to install Cabal now, or GHC now again, right?
Yeah.
So probably I should, at least in the meantime, I can also just clone it locally. So I go on code and do this, and then I go to the folder. Must just go up a bit because I'm inside our teacher repository. So this is my Haskell folder, and I can do a git clone and paste that in. And I hope this should be fast now, or does, I mean, Visual Studio probably also, I mean, locally I also cache, right? That should hopefully be fast.
Yes, that should be, yes, instantaneous. Hopefully.
Right, so I do code dot to open it.
No, but you open the Haskell repo.
Yes, I did. Silly me. So let's go into 3 and now do code dot. Right, and now, okay, now this dialog pops up, so I can do reopen in container. Whatever. So this should be fast now. I can maximize it. Let me just close the other one because Visual Studio often takes a lot of resources, especially this Haskell language server that does the IntelliSense and so on. Okay. Okay, I think this is done already. So that's really fast now. So, I mean, it takes a while the first time, but then later should be fast. So let me open a different terminal. Right. So now I'm in this, as already in the right folder. So that's good. I'm in the assignment folder. And now, I can, of course, do Cabal REPL to open REPL. So that should work. But I can also leave that. I can also do a Cabal build to build the project and see whether there are any compile errors. And especially in these first assignments, I think not necessarily in the later ones, but in the first ones, we also have tests. So I can do Cabal test, which will run all the tests. This now takes a bit because it has to install some packages needed for testing. But again, that's only needed the first time. So that should be reasonably fast. We'll also talk about how to test Haskell programs in a later lecture. But now we just use that as a given. That should be fast, I hope.
Maybe you also want to open a Haskell file so the server starts as well.
Sure. Well, the first one is data types.
Yeah.
Okay. Whatever. Okay, and I see now this is the output from the test. And I see 54 examples and 25 failures. So that's to be expected because before you solve the exercises, we only have dummy implementations, and then the tests that check whether your solutions are correct should all, mostly fail. I'm not completely sure why we don't get 54 failures, but yeah, whatever. But you get a lot of failures. So the goal should be for you to get 0 failures. Okay. Right. So now I could start implementing, and then I could either, yeah. So I should probably open a REPL, and I should load this module. So that's called data types. Right, and now I can read what I'm supposed to do. Okay, and logical. So the first task is logical implementation. And here we also see, I want to talk about testing. There's a whole dedicated lecture to testing, but I just want to show that this is a special type of test. Try to think. There's no easy way now for me to get the head is there?
To get a head of?
Let me just see what happens if I do Cabal head hoc.
Haddock, okay.
Actually, I'm not sure whether I can actually open that.
The index.
Okay, let's see. I can try to.
Can you try open the index HTML with?
Yeah, right. I can, but there's unfortunately no viewer. I think is there.
No, but on the browser.
Yeah, but this is in a container, so probably that won't work. Oh no, it should, because it's like yeah. Sorry. Yeah, I get you. Where is it in this?
8080, isn't it? Or
I'm sorry, I can.
8080, isn't it? The port.
But there's no server, is there?
It's
There's no head of.
Right. No, there's no server running, but there's a port to communicate.
But this folder should be reflected in my.
Oh, yeah.
If I go to my, if I look at this new style, that's where the compiler builds this stuff. So if I just, so it was build x60 Linux, whatever, GHD, data types. Okay, doc.
OPT doc.
Oh yes, sorry. Doc HTML data types. Maybe let me just. Okay, data types. Okay, there's this index HTML. So I think, can I just do Firefox or something, or open?
And maybe if everything is static, you may just you may only need to run open in Firefox.
Open?
No, Firefox.
Yeah. Okay, I can just. Okay, let me see.
And I will do index.
Yeah. I can do file. Let me see. Sorry. Why doesn't that work? A bit confused. Shouldn't that work?
Can you try?
I can try Firefox if that helps. Maybe Firefox works better for this.
No.
Sorry. It's weird. Normally, you can easily open files in.
Maybe if you can you try running Firefox on the path and on the terminal?
Yes. Let me try this. So index HTML Firefox. Okay, this worked. Right. So the point of this is now, I mean, until now we have only used Cabal REPL, right? So with Cabal REPL, I get into my interactive REPL, and then I can interact with my code, and I can ask Haskell to evaluate stuff. Okay, so that's nice. But this Cabal can do more. So it can't only open a REPL, it can also build my code to make it like, turn it into an executable or into a library. It can run tests, and it can generate documentation. And we'll talk about that in the lecture after this one about tooling. But the tool is called Cabal, so that's like the Haskell package manager. It's responsible for building your stuff. So it downloads the dependencies from Hackage. It's similar to NPM for Node, for example. If you do web development, then you often use NPM to get all the JavaScript libraries you need. And Cabal is basically this similar tool for Haskell. So Cabal REPL we have seen. Cabal builds your code. And Cabal I also showed you, so that runs your tests if you have any. And then there is also Cabal Haddock, which is a weird name, but Haddock is the Haskell documentation tool. And that builds documentation. And there are lots of parameters, but by default in HTML format. And here it says where it created it, so this folder. So I'm now just opening the folder, like the local folder in my browser. That's not the perfect way to do it. Better is to start a web server that serves the static files, and you have some more functionality. So we could also do that. But all I want to do is show you that we get this documentation now, which is quite nice. So I, for example, can go data types. And if I look back at the code, that where I was here in data types, I see that, for example, the first function is this implies, and I see the documentation here. So automatically, basically, it takes all the top level functions, and in the documentation shows me their signatures. And it's really nice because I also have, if you did it properly, now I built it locally and it's not really set up correctly, but there are also hyperlinks. So ideally, if I click on bool, it would take me to the documentation for the bool type and so on. And I could also, this is now just the function names and their signatures. So there's no text really. There is also something, probably we should talk about that later, but I can do some, there's a special, we talked about comments. I said that -- introduces a line comment. And for this Haddock, for this documentation, there's special syntax. So if I, for example, do -- space and then a bar, I can do this comment will appear in the Haddock documentation. So if I do this and if I rebuild the documentation, and maybe I probably have to refresh here, then this line I just typed appears here. Unfortunately, now it's a bit mangled. So let's do this again. No, that was not it. Sorry. I think I just need to blank there. Yeah, okay, so that's it. And I think we will talk in this tooling lecture, we talk more about Haddock. So we can do all sorts of things. I mean, you can have like hyperlinks to types and so on. This is very nice. So I mean, but of course, a lot of languages have that. I know .NET has it. So in C# you have something similar. There's a special, special syntax for comments, and then there's also a documentation tool, and then you get nice HTML documentation. I know it exists in Python, and I know it exists in JavaScript. So Haskell also has that. And the reason I'm telling you this now, I mean, first of all, it's nice, of course, because you can, it's a nice way to document your work. But you also have these examples. So you can basically add a documentation with this special syntax. So with this, whatever, greater, greater, greater. So the idea is it's an example. So, I mean, this is about this function implies. And you basically give an example and then say what the expected answer is. So that says if I enter implies false, false, then the answer should be true. And if I say implies true, false, the answer should be false. So far, so good. I mean, this is just text. It's just a documentation. But now there is a tool called DocTest in Haskell that takes these documentations and actually turns them into unit tests, basically. It actually runs this code and checks whether if you do implies false, false, you really get true. And if you do implies true, false, you really get false. And then if not, your test suite will fail. So it's like a living documentation. So you can embed simple tests into your documentation and they will actually be executed. And then you get a failure if what you claim should happen doesn't happen. So it's like a nice way to write tests, simple unit tests. And it's also a nice way to keep documentation up to date, because if something changes, if something suddenly, if some of the examples suddenly break, then when you run your test suite, you will get an error. So I mean, a common problem with documentation is that it gets stale, that it becomes wrong. And normally, I mean, wrong documentation is worse than no documentation. But DocTest is a nice tool to prevent that. So long story short, I think we mostly use DocTests here to basically do these tests. So right now, if you do implies false, false, for example, if I tried it, sorry, I must go back into my REPL, data types. So if I do implies false, false, I should, according to the documentation, get true, but I get an error undefined. And that's not surprising because the implementation of implies just throws an error. I mean, this is for you, that's part of your homework to define implies. So, but basically we see that's wrong. And when I run the test suite, it also catches that, and that test fails, which tries this. Okay, so now what was the task? We are supposed to implement this implies. And so here's the truth table. So implies false, false should be true, implies false, true should be true, implies true, false should be false, and implies true, true should be true. Right. And then there's the second remark, try to make the definition as lazy as possible and do not use other functions. So like a straightforward vanilla definition. Okay, I'm not sure I'm able to do this, but let's see. Let me maybe just do the one. Okay, fine. So what did we say? How do we implement functions? So the first step is give names to the arguments. I can call them whatever I like. I mean, normally you call arguments something like X and Y. Some people also tend to, I mean, they are like, I mean, it's subtle and folklore. I mean, in this case, because it's Booleans, maybe you wouldn't call them X and Y, but instead B and C or something, but doesn't really matter. So X and Y is fine. And now, I don't know. I mean, no way for me to do anything. So I must somehow split cases. And then, of course, I always have a choice. I mean, I can split into 4 cases, split on X and Y, but I can also only, I mean, maybe it's enough to split on X or on Y. So don't know yet, but let's just split on the first. So let me do false and true. Like this, okay. Okay, maybe now it's enough, maybe not. Maybe I must also split on the Y. So let's see. So if the first is false, then this table tells me I don't care about the Y, whether it's false or true. The result is in any case true. So I don't care about the Y. I can just say true. So that's already nice because at least in this case, I don't care about the second one. Okay, and now in the true case, so the first argument is true. Well, if Y is false, it's false, and if Y is true, it's true. So that means I also don't have to look at, I mean, I need the Y, but I don't have to split cases because it just returns the Y. So I can say this. And now I can, I mean, I could by hand try this now, these 2 examples. So if I do implies false, false, I indeed now get true. And if I try implies true, false, I indeed get false. And I could also, I exit the REPL and run my test suite again. And before I do it, I check what I got before. Sorry. Okay, this is it. Sorry, no, that's the documentation. The test suite was here. So I mean, before I got 25 failures, 54 tests, 25 failures. So now if I run it again, I still have 54 test cases, but only 24 failures. This here counts as 1. I think if I put a space in between, it would be 2 different ones. But anyway, so there's improvement. So I fixed 1 error, so that means I did something right for the homework. Okay. I'm not sure whether this is now as lazy as possible, but I think it probably is. And the nice thing is I never have to pattern match on the Y. So it will, I mean, it doesn't have to, even if Y is undefined, I mean, this wouldn't crash. So that's nice. It's lazy in the second argument. I don't have to pattern match the second argument in either case. In the first case, I can completely ignore the second argument. And in the second case, I just pass it on as the result. So I also don't have to look at the Y. So this is nice and lazy in the first argument, in the second argument. And I think in the first argument, I can't help but have a look at it. So maybe the second one we can do together. So what is the second one? I mean, I also don't intend to do the thing, then probably that would, but maybe like a couple at least in the beginning, and then maybe my colleagues can tell me whether there's anything else I should do. Right, but let's look. Yeah, sorry.
Yeah. So like one thing that some got wrong was the laziness part. They did the pattern match for the 4 cases.
I see.
So
Okay,
we
I mean,
covered the key the key concept.
Right. I mean, what I could do, of course, is I can just replicate this full truth table here, right? I mean, this truth table, I can just I mean, have all 4 cases. So, sorry. Let me just comment this. So I can just do the full truth table and just write it. What do we have? False, 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 true, and true, false, which is supposed to be false, and true is true. So this will also, and the formatting is not nice, but okay. If I do this, then also no, I was out of the REPL. So if I do that, so then the 2 cases, so that works. I mean, it's obviously correct. It's even more obvious than with my solution, because all I did was I just took the truth table from here and just copied it verbatim. And now for the laziness part, I mean, I think I already said that in Word. So if the first argument is false, we see in both those cases, I don't have to look at the y. It's in any case true. So I don't care if this is false or true, because the answer is anyway true. So I can just ignore this here. And if I do that, then I see I have this exact same equation twice, so I can remove one. So that's one. And for this, if the first argument is true, I see if the second is false, I get false. And if the second is true, I get true. So therefore, I can simplify that to basically this. I don't have to do the pattern match. And that's exactly what I did before. So that's how you might arrive at a lazier solution. So this will now in particular also work for undefined. So if I now do implies false undefined, yeah. Oh no, I must reload. See, with your solution, I mean, with the truth table solution, this crashes. But now if I reload, so now this one is active. If I try the same again, then I get true. So it doesn't crash anymore, because it doesn't look at the second argument any longer. If I now tried it with true, then it would crash. But the point is, it doesn't crash when it evaluates implies. It crashes when it tries to show me a result. So implies true undefined by this line is undefined, which is perfectly fine. But then because the REPL wants to show me the result, so it calls show on undefined, and that is when it crashes. So if I don't look at the result, so if, for example, I do something like true or implies true undefined, it also works. Whereas with the solution some of you had with the truth table, no, that also works. Yeah, that's maybe a bad argument. Anyway, this is better. Right, I'm not sure I want to do this implies prime. I'm not sure how interesting this is. Is there anything you can recommend me what I should do, Robertino or Karina?
As far as I know, that was the one conceptual wise. The others were either like wrong or not attempted or correctly made. So
right, okay.
And further along, it starts to build up on top of these first ones. So if you want to do another one, it should be one of the first 5.
Okay. I mean, this implies prime. I think it's not very interesting. I mean, it's just. I mean, if you have ever done logic at school or at university, then sometimes people even define. I mean, there's implication that A implies B is often defined as B, or often it's defined as not A or B. I mean, this is just, some people even introduce implication. I mean, they say, I mean, the thing people always get confused about with implication is what happens A is wrong. So the point is an implication is, I mean, also it's in this truth table. I mean, it has nothing to do with Haskell. It's just like logic. So you have this premise and the conclusion. So A implies B. A is called the premise. B is called the conclusion. And implication only says something. I mean, the only case is if the premise is actually true. If the premise is wrong, we don't care about. I mean, the implication is anyway right. So I mean, so for example, and that is something that some confuses people. So I mean, if you have whatever, if 4 is a prime number, then monkeys can fly. That's a true statement, because 4 is not a prime number, so it doesn't matter what I write here. This implication is true because the premise is false. Anyway, and because there is this definition, so A implies B is the same by definition as either the premise is wrong or the conclusion is true. I mean, we can just use that here. Basically, you can just take a logic textbook and just write it like that. So X, Y is just not X or Y. And I mean, we can try this. So we had this these two test cases. Implies false and implies true false, and the same results we should get with this other definition. Okay. So often, obviously, you don't have to define everything from scratch. I mean, you can, of course, normally use existing functions. But I mean, here in this specific assignment, it did say do not use other functions. But normally, of course, if you write programs, you would try to reuse existing stuff. And this actually would also be just as lazy. So if I do, I mean, implies prime, false, undefined, it also correctly says true, because or the logical disjunction has the same laziness behavior as this here, that it is lazy in the second argument. I mean, we have done that in the slide, so maybe I shouldn't do the or else, right? And then
Yes.
maybe
From the next ones, there are a lot that are re-implementing what we already saw in the slides.
okay. Speaking of these weird operators with the dollar and so on, I think this is now the time where I want to introduce the dollar operator, because it drives me crazy that I haven't yet. So there's an operator that is used a lot. I use it all the time, but we haven't talked about it yet. And it's called dollar. And the definition is a bit weird. So if we look at the information for dollar, so it takes a function from A to B and an A and returns a B. And the interesting thing about the dollar is actually this one. It's right associative, and it has precedence 0, which is the lowest possible precedence. So everything else has higher precedence. And for a beginner, I mean, when I saw that the first time, I also didn't understand what that's supposed to do. So first of all, how is dollar implemented? It's just function application. So if I, for example, let's look at a function. What's a nice function? Even. So if I have even 8, so it's even, sorry, is 8 an even number? Yes. And even 3 is false. Well, it's just where I can put a dollar in between, and I get the same results. So the dollar does nothing more than just apply a function. So only, I mean, in the very beginning, I told you in Haskell, function application, we don't need parentheses. We just write the function, a space, and the argument of the function. And instead of doing that, you can also write the dollar instead of the space. So of course, the question is, why would that be useful? And the reason is precedence here. So often we have something, that's a good example. Let's say I want to, I don't know, let me import this data.character. So I have this two upper and two lower. Let's say I want to do something like map to upper, and then I want to do Haskell Nairobi, something like this. Okay. What now?
Yeah.
Okay, I see that's hidden. Never mind. There's another way to write this. I can also write this. Never mind about that. Doesn't matter. This is a different word, way to write plus plus. Okay, and this is a little bit annoying because I need these parentheses, and Haskell programmers don't like parentheses. So the reason I need them is if I don't write them, if I do it like this, then I will get this. So the reason, if I write that, then the function application binds very strong. So if I write this, it would be interpreted by the Haskell parser like this, which is not what I want, right? So I need these parentheses here. But if I instead use the dollar, sorry, I can write it like this. Sorry, like this. So the dollar helps me to avoid parentheses. So if I can basically, I don't need the parentheses if I can just use the dollar, because the dollar is so low precedence, everything. So I could also do, I don't know, no, I can't do that. No. So normally you can only do it for the last, sorry, forget about that. But for the last argument, and that is often very useful because then you can, especially with nested parentheses. So I try to think. I know in the lectures I was often tempted to use the dollar. But maybe don't worry about it now. But now I've told you, next time I use it, then I can point it out, and it can be useful all the time. So you wouldn't need dollar. You can't write any function that you can't write without it because it's just function application. So the only point of the dollar is to make it look nicer because you can avoid parentheses. And you often can avoid quite a lot of parentheses by using this dollar. So it just declutters your code. Doesn't do anything new. It just applies a function. Okay. So should I do something else? I'm not sure.
No.
Maybe if someone has a specific function that is having troubles with, we can ask now, else we can move on.
Yeah, or maybe for the not for this homework, maybe for the other homework, because some of them started the homework maybe yesterday.
Okay. So should I then continue with the lecture?
Yeah, I think so. If someone is having specific troubles, please ask now or maybe later in Telegram and we can revisit. But because we don't know where are you having trouble, I think it's safe to assume that we can move on.
Okay, good. Let me move on. Actually, there's an hour over now, so it will be time for a break, but I can maybe at least start. Okay, I closed this on purpose because as I said, I don't want to have too many Visual Studios open. Now let me open the lecture thing again. Reopen it in container. Let me close this. Let me go into the right folder. So we're now starting with, we had lecture 4, we completed that. So now it's lecture 5. Let me just open this. Let me also navigate into the right folder, lecture 5, and start a REPL. And let me leave it like this for a second. Oh, okay. Okay, and let's switch to the slides. So higher order functions. Okay, and so we will look at some particularly useful higher order functions. So the topic is in particular, we will look at so-called folds, right folds, left folds, fold right, fold left. Then generalize that to other data structures. Then generalize the map function that we have seen for lists, and generalize fold R to other container types. That all sounds very abstract, so let's start. But before we talk about that, we talk about higher order functions. And this is basically the same slide we just saw as the last slide of the previous lecture. So I just skip over that. Meta map. So I think this is just right. So there's some duplication in the lectures, in the slides. But this one is new. So function composition. So there's a operator in Haskell that's just the dot. And it's defined like this. So f gx equals f of gx. So let me just, it's hidden. Okay, it's defined here. Let me just comment this out. Probably I get some, no, I don't. I forgot what I need proof for, probably as some example later. Anyway, never mind that. So normally the dot operator is in scope. It's in the prelude, but let's just define it. So f dot gx is f of gx. So that's the definition. And this is not even Copilot. That's now anyway. Why do I get an error there? Okay, because I didn't give a type signature. Oh, by the way, this would be a prime example where I could use the dollar. So I have these parentheses here. So alternatively, I could write it like this, and then I get rid of the one of the pair of parentheses. So it means I first apply G to X and then F to the result. So what's the signature? And I mean, it's already, I mean, the editor already told me. It's annoying, but let me just delete this. Just as a, like another example, how the compiler can figure out the type of things. So we want to define this dot, and I want to write the signature here. What is the signature of dot? Okay, and I have no clue, but I mean, here's the definition. And no matter what it is, so it takes an F and a G, fine. So it takes an F and a G, and an X, and it, I mean, so the F and the G, so it takes an F and a G. So it takes an F and a G, so it's a function of 2 arguments. And what's the result? I don't know. I mean, whatever it is, it must be a function, because here I'm applying it to X. So the result is actually a function. Okay, so it looks something like that. So now let's see. Let's call the type of X. I mean, I don't know anything about X. Let's call that A. So the type of X I call A. Right, now here I see in the definition that whatever G is a function because I apply X to it. So I can refine what I know about G. It must be a function. And I apply it to X. And I said that X is of type A. So whatever G is, the argument type of G is A, the type of X. Right. Now F. F is also applied here via dollar or the previous version to something. So F is also a function. So I can refine this to that. Okay, so what is the argument? I don't know, but it's, I mean, I'm applying it to GX. So I'm applying it to result type of G. So let's give that a name. Let's call this here B. So if I call this B, then F takes a B and puts it into something else. And let's call that something else C. And then we say C, okay, F is a function from B to C, G is a function from A to B, X is of type A. So what I get is first I apply G to X, gives me a B, then I apply F to that B, and I get a C. So in the end, I get a C. So this is the type of what? Why do I still get an error? Oh yeah, because I'm not exporting it. Fine. Anyway, so this is the signature. Just as a recap, how the compiler can figure out that signature automatically. So if I do this and if I now ask, it will give me this signature. It will just skip these parentheses because they are not necessary because the function error is right associative. But I think writing it like this makes it clearer. And I also always feel a picture helps. So we have our F, which goes from B to C. And we have our G, which goes from A to B. And then, sorry, that's probably, yeah, no, sorry. And then F dot G goes from A to C. So, and it's, I mean, the definition is very simple. So you have a function from A to B and a function from B to C. And how do you turn that into a function from A to C? Well, in A, you first apply the first function, and then you apply the second function. In mathematics, that's called function composition. And then, of course, you may wonder why it's the wrong way around. I mean, why is it F dot G and not G dot F? And that's a good question. And the reason is that somehow in mathematics, we think the other way around. Well, actually, the reason is this, that it's the same order as when you write this. I mean, on this side, it's also in that order. But maybe the best way to picture it is to write this the other way around. So the G here and the F here. And so just turn the picture around. And it looks nicer. And that basically better explains, I mean, the order. So that's how you would normally draw it in mathematics. So you have a function from A to B and a function from B to C. You can compose those two functions into a function from A to C. And it's very simple. You get an A, you first apply the first function to get a B, and then to that B, you apply the second function to get an F. And I mean, you can try this. So for example, let's say G is even, the even function from, let's say, int to bool, and F is not from bool to bool, we know. So now I can use this. So that would now the special case A is int, B is bool, C is also bool. So now I can, for example, do F dot G of 6, and it's false because why? Because first I apply G, the even function, so 6 is even. So I start with 6. G is the even function, so I get true. and then I apply not, which turns that into false. So if I start with an odd function, then G maps it to false, and then not maps it to true. Of course, the types don't, I mean, in this case, B and C are the same type. Of course, that doesn't have to be like that. What else can I do? For example, I can do length from, let's say, string to int. Okay, and f even from int to bool. So now A is string, B is int, C is bool. So if so now I can apply f.g to, let's say, Haskell. I get false. Why do I get false? First I apply G, so the length function. So length of this list, that's 7, I believe, 7 letters. So G of Haskell is 7. And to the 7, then I apply the even function. 7 is not even, 7 is odd, so I get false. So that's why the result is false. And if I take something like, I mean, if I leave one, whatever, Java, then we get true, because Java, the length is 4 and 4 is even. So like this. And I mean, by definition, this is also exactly the same as if I had, I mean, not used the dot, but simply applied the functions like this. I mean, this is by definition of the dot the same. And so this is very, and I mean, in other languages, something like that might be called like a pipeline, for example. So you have several functions, and with dot, you can apply one after the other. So you basically have a like processing pipeline of your data. And I think there's an example on the slides. So I did this type inference stuff. Here's the picture, how that's sometimes depicted. It's similar to what I tried to do there in the comment. And here's an example. So let's say you have the task to compute the first 100 odd square numbers. I don't know whether you have seen the take function again, probably in the exercises. So there's a function called take in the prelude. It gets an int and a list, and returns a list, and it takes the first so and so many elements of the list. So if I have Haskell, which is a list of characters, I can do take 3 Haskell, and it just takes the first 3 characters. Of course, it doesn't only work for lists of characters, it also works for lists of anything. And if I take, I mean, more than the list is long, if I take 100, I just get the full list. Okay, so that's take. That's a very useful function. I'm sure it's mentioned in the exercises. Just give me a second. I'm sorry. There's somebody at the door. Maybe we can have a short break now for 10 minutes.
Yeah,
Is that-
sure.
Yes.
Okay. Thank you. Let me. Okay, then we continue at 1:30.
Yeah.
Okay, shall we continue? Sorry about that. Had to accept the delivery quickly.
Yes, if you can, let's continue.
Okay, I am. Let me share again. Okay, where were we? Okay, computing the first 100 odd square numbers. And I can nicely solve that with the dot. And that's also a nice example of laziness if I want to do it. Because, I mean, it's a little bit, I mean, because of this odd thing, I don't really know. I mean, probably it's something like the numbers from, I mean, I probably need to square the numbers from 1 to 200 or 201 or 199, I'm not sure. And I'm too lazy to think about that. So I can just start with all numbers. I mean, infinitely many. So that would be this. I talked about this dot dot before. So if I have something like this, I showed that before. Sorry, it's of course not an integer. It's a list of integers. Then I get the numbers from 1 to 10. But I can, so what I think I haven't mentioned before, I can also leave this. And then it's all the integers starting at 1, going on forever. So if I press enter now, my REPL will be an infinite loop. So I must press Control C to get out. And we see, I mean, time it took me to press Control C, it already got to the number 102,788. So it would now continue until I press Control C or if it runs out of memory or whatever. So I can basically start with this. And in the end, I want, let's say, a list of integers. I mean, I could also take int. So now the idea is that I apply some sort of pipeline of functions to that to get my answer. So I want square numbers. So the first thing I want to do is square each of those numbers. So I can do that with the map function. And in order to square, I can just use a lambda. So x gets mapped to x times x. So if I did this, I would get the list, the infinite list of all square numbers. I mean, I can do that quickly if I want to. And I mean, I'm too slow to. Yeah, okay. I mean, you get the idea. So that's now all square numbers. So now I want only odd square numbers. So I can use filter afterwards to filter the odd ones. And now I can use this pipe thing. Must just put parentheses around this. So now I have the list of all odd square numbers, infinitely many. I'm only interested in the first 100, so I can compose this with take. And what now? Oh, it's not in scope because reasons. Let me just put it back into, sorry. Let me reload. Okay, and there you go. So this would be an example of, I mean, this is of course toy example, but I mean, how you can easily like compose or answer a relatively complicated question by composing simple functions. So I just start with the list of all numbers starting at 1, all integers, 1, 2, 3, 4, 5, 6, forever. Then first I square each of them using the map function. Then I compose that with filter out the odd square numbers. And finally, I compose it with take 100 to only keep the first 100 results. And this is also a nice example of laziness because even though I start with an infinite list, I end up with a finite one. And I mean, Haskell has no problem giving me that finite list because of laziness. It only needs to compute the first 100 elements of this list. So I don't get it in infinite loop, even though I have a potentially infinite list here. And of course, I could write this also without the dot operator. I mean, until today, we would have written that something like so. So I first apply map, then I apply filter odd. And then finally, I do take 100. I mean, this gives me the same thing. And now that I told you about the dollar, I mean, this would be a prime example of where you would want to use the dollar. I can get rid of a couple of these parentheses by using the dollar instead. So this also gives me the same. And this is more or less a matter of taste, whether you write it with a dollar or whether you use this dot composition. Nevertheless, that's like one main thing to write functional programs to I mean, a functional program is basically just a very complicated, I mean, potentially very complicated function, depending on what complicated problem you want to solve. And I mean, one technique is divide and conquer. So solve your complicated problem by splitting it into many simpler problems or simple problems. And then you can, I mean, ideally just solve the complex problem by doing a series of small, simple steps that you compose, for example, with the dot operator. I mean, of course, in reality, normally it's not that simple, but that's the general idea. So let's see in the slides. So yes, same I did. Start with all numbers, map, I mean, square all of them, filter the odd numbers, the odd square numbers, and then take 100. So we end up with this. And as I just said, so by using composition, you can split a complex problem into simpler problems. I mean, this is now a special example, this dot operator, but the same or similar is true for other higher order functions. They often give you a way to compose a problem into simpler problems. And I mean, and of course, if you have something like map or filter, that often appears, and it's useful to know about those and to have them in your toolbox because you can use them all the time. And basically, of course, we can always solve basically all our problems with the standard design pattern on list that this lecture on last Friday was about. But often you don't have to. So you don't have to basically by hand define the function. Often you can solve a given problem by using existing helper functions like map or filter or function composition. Oh yeah, and I mean, one way to look at it is that function composition is a bit like functional semicolon. So in imperative standard programming languages, often you have this semicolon at the end of a statement, and the semicolon like splits statements. I mean, you have something like, I mean, step 1, semicolon, step 2, in another language. Often, of course, in different lines, but often you can also write it like this. I mean, in one line. So, and then in a like normal, like in Python, you would execute step 1, then step 2, then step 3, then step 4, and basically the semicolon separates the steps. And this is very similar now in Haskell, except it's the other way around. So in Haskell, it would be like step 4, after step 3, after step 2, after step 1. So in this sense, function composition. So first do this, then that, then that, then that. So apply this to your input data, then that, then that, then that. So in that sense, this function composition is a bit like a functional semicolon. I wouldn't take it too seriously. And this I have now also said several times, because of laziness, we can basically solve a problem by splitting it into first generating possible results and then selecting interesting ones. We don't have to worry too much about how many potential possible results we generate first, because laziness will only ever compute as many as we actually need to come to our answer. And this means we can make our programs modular. So we can basically write one, we first concentrate on generation, and separately from that, we can concentrate on selection. And then we just compose the two parts together. And using techniques like partial application or anonymous functions, we can keep that concise. So, I mean, this was an example. This, for example, an example of partial application. So filter takes two arguments, the predicate and the list, but here we partially apply the predicate, and this is now a new function that, given a list, filters out the odd elements. Same, this one, map, also takes two arguments, the function and the list. So by partially applying this square function, we now end up with a function that maps a list to the list of squared elements. Similar for take. And this is all very short and concise. Okay. So we have that. Okay, let me just see. I mean, most of that we have already seen. So there are some helper functions that are often useful that turn one function into another function. So one function we haven't seen yet is flip. So it takes a two-argument function from A to B to C, and turns it into another two-argument function, which is now from B to A to C. And the definition is very simple. So flip f x y is just f y x. So I just flip the arguments around. And that can sometimes be useful. I try to think of an example. I mean, we can again use this filter, for example. I mean, we have filter odd this. And if for whatever reason I want to swap these arguments, I mean, like this, it wouldn't work. It would be a type error. But if I flip, then now I can give the arguments in this order. So sometimes that's useful. Another example would be maybe a little bit better example. So if I import data list again, earlier that I have this sort by function. And if I wanted to sort descendingly, I set x and y, compare yx. And for example, I applied that to Haskell. And then it sorts it in descending order. So now that we know about the flip function, I can write this more concisely by just saying flip compare. That would be a use case for this flip function. Right, so we saw it. Yeah, this is maybe a good example. I mean, you could define this for each flip map. I mean, often you have a situation, or sometimes you have a situation where you have a given list. Let's say XS is the list of numbers from 1 to 1,000. Let's say int, sorry, list of int. List of int, fine. So let's say I want to do something complicated with it. I want to do x time plus I don't know, something like this. Why do I always get 19? Oh no, I don't always get. Okay, fine, whatever. Just a silly example. So this is sometimes so sometimes it's, or normally it's more convenient to have like the most complicated argument at the end. So using this for each now, I could instead write for each, and then the list comes first. And this doesn't really change much, but now using the dollar, I can get rid of these parentheses. And that gives me the same result, but it's someone better to read. And it's also more like, I mean, maybe more familiar to people. It's almost like a for loop or for each. I mean, that's also exists in JavaScript or TypeScript. So basically do something to each element of a list. So yeah. Right. And curry and uncurry, I think, don't really talk about it because we have had that already. I talked about that at length already. Yeah, what's the question?
Yes, I have a use of case of that flip operation. For
Yes.
example, if we have a function with a parameter at the end, and we can get rid of that parameter using the flip operator by just I don't know, for example, the next one, if x param is equals to
Are you typing something? Sorry.
yes,
Okay. In the chat or where?
yes, in the chat.
Okay.
For example, something like this,
Mhm.
and we can get rid of the second one, right? Or the first one by flipping the operators and just getting rid of the parameter.
Right.
I don't know if I explained.
Yeah, I think I know what I mean. One thing is, one thing maybe you mean that. For example, let's say we want to divide each element in a list by 2. We could do. Is that a good example? Div x2. Sorry, forgot the lambda, the backslash. Right. Okay, fine. And but I would also like write this instead with flip, as I think that's what you mean. I could write it as flip div 2, and now I don't need the x anymore.
Right.
Because yes, I think that's what you mean. In this specific example, probably, I could also write it using this backtick thing like this, and I again would get the same. But yes, you're right. That's one use case.
Okay. Okay.
Thank you.
Thank you.
Good. You're welcome. Good point. Right. Okay, I talked about curry and uncurry already. So let's leave. But maybe what I should mention is this zip, which appears here. I'm not sure whether that was in examples already, because that's often a useful function. So zip takes 2 lists and zips them together. So maybe the best is to just show it. So if I have zip, for example, the integers and Haskell. So it takes 2 lists of arbitrary element types, and then zip turns them into a list of pairs. So it zips, it's like a zipper. It zips the first element of the first list with the first element of the second list. So the first element of the first list is 1. First element of the second list is capital H. So the first element of the result is the pair of 1 and capital H. And then it takes the second element of the first list, 2, and the A, and pairs them, and so on. And the 2 lists don't need to have the same length. So in this example, the first list has infinite length and the second list has 7 elements. So it stops as soon as you run out of elements with one or the other list. And then in this example, if you, for example, have 2 lists of numbers, let's say from 1 to 10, and again from 1 to 10, and you would like to build a multiplication table or something to multiply all. No, that's a stupid example. Let's say, what do they have here? It doesn't matter. 1 to 3 and 4 to 6 doesn't matter. So let's say you want to multiply each element. The first element of the first list with the first element of the second, this second element with the second, and so on. And then you could do it with map, but now you must uncurry star like this. So now 1 times 4 is 4, 2 times 5 is 10, and 3 times 6 is 18. And I need the uncurry here because now star goes from A to A, but now I have pairs of numbers. So by uncurrying it, I can turn a function operating, a curried function, 2 arguments into one that operates on pairs. So that's this example here. But the zip is also very useful often. Right. So that's just some useful functions, flip, curry, uncurry. But now let's talk about folds. And one thing that we try to do a lot in Haskell is to recognize patterns that we use more than once or often, and then somehow abstract those patterns away, give them a name, implement them in some library, and then you don't always have to write the pattern by hand, you can use it. So, for example, functions on lists. I mean, we have had many examples of functions on list, and we the standard design pattern of function set. Okay, normally if you want to define a function on lists, you need to consider the two cases, case of the empty list and the case of the non-empty list, where you have a head X and a tail X's. And so for the non-empty list, you must do stuff. Sorry, for the empty list and for the non-empty list as well. And often this will recursively call the function you're defining on the tail. So normally what you do here, this ... is something that uses the head and the function recursively applied to the tail. And we saw lots of examples of that. So for example, map or filter are examples of this, where we use this pattern. Now, when you see something like that often enough, then as a Haskell developer, you have the urge to like extract the pattern from that. And these ... dots, of course, that's no valid Haskell. But let's try to like turn this into proper Haskell now. So let's do this. So we have this ... and here we have that ... So of course, ... is not valid Haskell. So the first step is let's give that names. So we call this ... nil and this ... cons, because I mean that's the traditional names for the empty list and the cons case. But of course, you can pick arbitrary names. So instead of ... we write nil and cons. And as we said before, this cons can make use of the head and recursively applying the function we are trying to define to the tail. And if we do this, I mean, probably I should do this. I don't know. So let's do this. So we are writing, we want to define this function, and we realize, so we have, I mean, let's say, a list of A's, and we want to get the B. And we know we normally do this by splitting into two cases, doing something for the empty list, doing something for the non-empty list. Okay, this is of course not valid Haskell, so that doesn't even pass. So now the idea is to give names to this ... So this is just a constant. We call nil for now. And here we call it cons, but we know this cons can make use of the head X and the function we are defining applied to the tail. And this is again something where I personally would use the $. Okay, this is fine, but now of course suddenly we have this nil and this cons, and just cheat quickly. Okay, so we have this cons and this nil that are not defined. So right now I get, I also get annoying tips, but anyway I also get errors because cons and nil are not defined. So if I want to do this, I must somehow add them as arguments to my function. So cons and nil, cons and nil. Okay, so now the question is, what are the types of these? And I actually can figure that out. So in this case, the nil is on the right-hand side, and I'm defining, I mean, here it already tells me it must be of type B, because, I mean, I want to get a B, right nil, so nil must be of type B. So this nil here must be of type B. Okay, and what about the cons? Well, it's a function of 2 arguments, so it has this shape. Right. The first argument is the head of the list. So I have a list of A's. So the first argument is an A. And the second argument is the function I'm defining recursively. Oh, sorry. And here I, of course, now also have these 2 additional elements. So it's the function I'm just defining applied to the tail of the list. So the result type of that is B. So the second argument is B. And at the end, I must get something of the right type of type B. So this is that type. And now it's just blue because it says that's like a built-in function. Just a second. For some reason, must just connect myself to power. I thought I was connected to power. Some reason. I think it's not. For some reason, power is not working. Just 1 second. Okay, now, sorry. Right. Okay, this is just because that's a function that exists. And now I can simplify a bit because here I don't need this con, so I could replace it with an underscore. And then traditionally, let's see what on the sides. So I did this stuff. Right. And this is normally called not fun, but fold R. Okay. Fold R. And now it complains because that's defined, but I am hiding it. Because of this thing. Okay. What is this now? Okay, fine. Okay, so this is actually defined in the prelude, and it's called fold R for right fold. And fold, it's called a fold because you basically fold a list of values into one result. So it's like aggregate. I think in JavaScript, it's called aggregate. And I mean, an example would be, okay. Right. And there's another thing now, just some new syntax for you. So we, speaking of local variables, I showed you this let construct. So for example, if you want to, I don't know. I mean, we can do things like let x equals 3 plus 4 and x times x. I showed that before. So that's one way to introduce local variables. There's a second in Haskell with where. So I could alternatively write this here as follows. So fold right cons nil equals go, where go empty list is nil, and go xxs. Sorry, go xs. Right. So where is another way to introduce local variables or local bindings. So this go is a local definition that is now only available here in this function definition. And it's more or less a matter of taste whether you prefer let or where. But it's not exactly the same. I mean, technically, it serves very similar purposes, but let is just an expression. So everywhere where you use an expression, you can use let. Where is a statement, so it can't appear everywhere where let does. I personally normally prefer where, because I find this let in a bit cumbersome. But anyway, so this is just another way to write that. It makes it shorter because I don't have to repeat this const nil everywhere. Right. So the idea is, in the empty case, I mean, I get basically two constants, the nil and the cons. So nil tells me what to do for empty list, and cons tells me what to do for the non-empty list. And for the non-empty list, I first recursively handle the tail, and then I use the cons argument to take the result of the tail, and the head to produce the result of the overall lists. I'm sure there are. Right. And the point why we can use where here is because the constant, the nil, doesn't change. In our old definition, we had the same constant nils everywhere. So therefore, we can write this a bit nicer by introducing this go function. So we don't have to repeat ourselves. Oh yeah, and one example is length. So let's look at an example. So we had the length function that takes an arbitrary list to an int, and we said the length of the empty list is 0, and the length of the non-empty list is where we recursively take the length of the tail and add 1. No. I must hide the existing one, otherwise we get cache. And I don't really care what this x is. I mean, that we saw before, that we saw even in the introductory lecture. So, and this uses this design pattern, right? It's the standard pattern. So we do say what happens for the empty list, and for the non-empty list, we recursively call it on the tail. So that means we must be able to write that as a fold right. So let's do this. So we must just figure out what nil and cons should be. So nil, as I said, is the result of the empty list. So in the case of length, the result of the empty list is 0. So the nil is 0. So what's cons? Cons is the function that gets the head and the result of the tail and gives me the result of the list. So in our case, it must be a function. And what do we do? So the result of the tail is here, this recursively called on the tail, length xs. And now with the head x and the length of the tail, what do we do? Well, we add 1. So this is the function that takes the head and the tail, the head and the length of the tail. And what is then the length of the list? Well, it's n plus 1. So we don't really need the x. So we could write it like this. I'm not sure how it's written here. Yeah, it is like that. Okay, fine. Let's first try that out. So length Haskell, for example. Okay, I must hide that here as well in the REPL. Data list. Let me just start that new, because I imported this data list, that makes it a bit cumbersome. So let's try this again. Okay. Okay, so that's a first example of fold right. So again, the idea is the process normally is we have written a bunch of functions on lists, and it always followed the same pattern. We wrote one equation for the empty list and one equation for the non-empty list. And in the equation for the non-empty list, normally we recursively call the function on the tail of the list, and then somehow use the head and the result of this recursive call to get our final result. And now the idea of fold right is to abstract that away. So we know we just need the result for the empty list, and we need a way to, given the head and the result on the tail, to compute the overall result. And length is an example of this, because length exactly follows this pattern, the normal definition of length. And so for the empty list, we have 0. So this nil argument would be 0. And given the head of a list and the length of the tail, how do we get the length of the list? Well, we add 1 to the length of the tail. And another way to write this here, just for giggles, is to use the const function. So I could write it like this. And we could even be cute and write it, sorry, like this as well. This should give the same result. Okay, so that's one example of using fold R. Another way to look at it is if you have a list. I mean, that's, I think, also on the slide somewhere. So if we write the, I don't know, don't have a funny, let's do this. I mean, this is not valid Haskell. Let's say that's cons, and we have our nil. And now if I apply that to a list, then it's a const b. So basically, I mean, one way to think of it, and I mean, we know this is just syntactic sugar for this. So one way to look at fold R is it takes a list and replaces the empty list with nil, and each cons with this operator, with the first argument that we called cons for exactly that reason. So in the case of length, to demonstrate that for length, so we start with Haskell. So that's, I should have started with Tom, but wouldn't have had to type so much. So this is like written Haskell, not using the nice list syntax, but spelling it out. And now the fold right const +1 near, sorry, in 0 of that, of Haskell. I'm not doing it again. So basically, as I said, you replace each cons with this, and the end with 0. We would get, I mean, for the H, we would get, sorry, allow me one more step. So there's a word, there's something called suc, that's on the enum class. So it's the successor. So for example, the successor of 7 is 8. So even better, I can write this as suc. So that should still give us 7. Right. So basically, this is now gets replaced with suc for the H, suc for the A, suc for the S, suc for the K. And somehow I should write it like this. H, suc, A, const suc. I don't know how to write that. Sorry. It would be better if it was an operator. Okay, let me define one. Sorry, I just want to forgive me. What can I call that? End. From A to int to int. That probably exists already, right? Not sure. Oh yeah, sure, that's logical. I just need a name for some, it doesn't matter, an operator name. I just take 3 ampersands, right? Sorry, I just want to, so a n equals n plus 1. So that's the function, that's this cons, right? That I'm using here for length. So that I now wrote as cons suck. So given a head and the length of the tail, what's the length of the list? I ignore the head and I add 1 to the length of the tail. I mean, that's the same that I wrote cons suck here. The point is just I want an operator for that because now I can write that nicer. Let me remove this stuff here. And this. So now I can, instead of cons, now I can write ampersand, ampersand, ampersand. And what basically fold R does is this. So it takes H, ampersand A, ampersand S, ampersand K. I really should have used E. Almost there. Yeah. And now the nil, which is 0. So this is, I mean, how people sometimes visualize what fold R does. So one way to think about fold R is it replaces the empty list with the nil argument, the second argument of fold R. In our example for length, that's 0. And it replaces each cons with the first argument of fold R, which in our example is this cons suck, which I also named ampersand to be able to write it in operator form. I mean, you don't never have to write that. So that is like a nice picture because you see, so the computation is you start with 0, and then for each you start on the right end of the list with the second argument to fold R, so 0 in this case, with 0, and then for each element going left of the list, you apply this cons operation. So L, L, E, K, S, A, H. And in this example of the length function, the actual letters are completely ignored, and all this function does is it adds 1 to the right argument. So we start with 0 here, 1, 2, 3, 4, 5, 6, 7, which is the length of the list. And this is, I mean, why is it called fold? I mean, the idea is you have this list, I mean, this container of stuff, this list of letters, and you fold it into a number in this case. So you like turn a list of things into one number. It's like aggregation in JavaScript or in SQL or so. And why right? Well, because you start at the right, basically, and then you apply the aggregation function in turn for each element until you reach left end. And you can do lots of things. I mean, length is one example. Let's look at another example, I hope. Okay. Let's do one. Yeah, okay. So we have this plus this concatenation. So taking a list of A's and another list of A's and concatenating them. This is probably also let's see. Okay, so they claim that this is the answer. Interesting. Okay. So I'm not sure whether I want to, like, let's just think about that. So what does it say? Can I at least write this? So the claim is that if I want to concatenate x's and y's, it's the same as fold right cons y's x's. Okay, let's see whether it works. Yeah, okay. So why does that work? So this is this nil argument. So the claim is if xs is the empty list or the empty string, then the result of concatenation is just y's, which is true. If I concatenate the empty list with something, then I just get this something. So that's that. And now this says if I have xs concatenated with y's, that's the same as recursively concatenating x's with y's, and then consing x to it, which is correct. So if I want to concatenate a list that has a head and a tail with another list, I can first concatenate the tail and the other list, and then const the head of the first list in front of everything. So therefore, I could have defined this plus plus as a fold right. And here are other examples on the slide. Filter, so is also a fold. So the second argument is always the result of the empty list. So what is the result of filtering the empty list? Again, the empty list. So the second argument that we called nil is the empty list. And now we need a function given the head of the list and the filtered tail to produce the filtered result. And that depends on whether the head of the list satisfies the predicate or not. So if it does, then we keep it and put it on the filtered tail. Otherwise, we throw the x away and just keep the filtered tail. So filter can also be written as a fold right. And finally, map, our map function. If we map over the empty list, we just get the empty list. And if we have a non-empty list with a head x and the map tail is r, then we just apply the function, you just get the function applied to the head to the mapped tail. So we could write map like this as well, as a fold R. So now the question is, should we? And that is also a matter of taste. So sometimes, I mean, this looks not as clear probably as the original definition I gave you for filter, or map, or for concatenation. So that would argue that it's like better to not use fold right and instead spell it out. On the other hand, that's also a matter of experience. So the more experience you get in Haskell, the easier it will be for you to read these things. And it also gives a hint to your to somebody that wants to understand your code. By explicitly using fold right, you are basically saying, hey, here I'm using the standard design pattern on lists, because that's what fold R does. It looks at the standard defined pattern on lists and abstracts it away as a function that we call fold right. So that means that, I mean, so somebody trying to understand your code doesn't need to, I mean, we did see examples once at least, I think, for this all equal function that didn't follow the standard design pattern of list, where we had three cases. We had the empty list, the one element list, and then lists with at least two elements. So that didn't follow this pattern. Normally, if you just write code, then it's not obvious at a glance whether you follow the standard pattern or not, whether it's something like all equal or not. But by using fold right, you basically make that explicit that you're using the standard design pattern, which can also make it easier for people to understand your code. So it's not completely clear. I mean, in this case, for example, for filter, I would argue this is more complicated than just writing down the equations. Here's a cute example. And not sure we have seen the and function yet, so that the and function takes a list of booleans and checks whether all of them are true. So and true, 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 true is true. But if at least one of them is false, then it becomes false. So and is a fold right, and it can be written very concisely as this. So this means and on the empty list true, which it is. So all elements in the empty list are true because there is no element, so that's true. And if you recursively know whether all elements in the tail are true and you have the head, then in order to figure out whether all elements are true, you must and the head with the recursive result on the tail. So you can very concisely write and as fold right of and, yeah, it's also called and logical conjunction and true. And then dually there's also or, I think. So or checks whether at least one element is true. So or of this would be false, but if at least one true is there, it becomes true. And that I could equivalently write as fold right this. So for the empty list, it's false. And then recursively, I do look at the disjunction of the head and recursively calling on the tail. Another useful function that we did talk about already is any. So any gets a predicate and checks whether an element in the list satisfies the predicate. Okay. It's that's what it's supposed to do, but I hide it here. So we can define that also with fold right. So given a predicate and the list tells me whether the predicate holds for at least one element in the list. And this is also a fold right. So first for the empty list, is it for the empty list given a predicate and an empty list, is it true that there is an element in the empty list that satisfies the predicate? Well, no, because there is no element. So in particular, there is none that satisfies the predicate. So now if I have a non-empty list, so I have a head and I have the recursive result. So I know, so R tells me whether in the tail of the list there is an element where the predicate is true. So giving this the head and this recursive result, what's the answer for the whole list? Well, I can be lucky that the head satisfies the predicate, or I can hope that some element in the tail satisfies it. So this would be an definition using fold R for any. And now this works. So it now found the 2, but if I make that odd, then it's false. Another example would be adding all elements in the list. So it's one of the classic examples, even though it's not a very good one. So I could do this. That would just add all elements. So the empty list, sum of the empty list is 0. And then to sum all elements of the list, I recursively add the head to the sum of the tail of the list. So 9 plus 3 is 12, plus 5 is 17, 24, 137. Yeah. I could do this with multiplication, but then of course the product of the empty product is 1. So this should be 1 and now 9 times 3 times 5 times 7 times 113, but I can't do that in my head. Okay, so a lot of things are right folds or folds. So, I mean, the advice here given on the slides is that if it's easy to write it as a fold, you should. So, and for example, is easy to write as a fold. It's very concise. A plus plus is also very concise, so probably you should write it as a fold. And as I said, one of the advantages of using that is that you signal to the reader of your code that you're using the standard design pattern on lists. And then there are others where you can write it as a fold R, but it's not really clear. So like filter, I would argue it's not very pretty to write that as a fold R. You can, but maybe you shouldn't. Okay. So are there any questions at this point? So fold R is quite useful. Although I would argue that even more useful is what we do next. Yeah, there was a question.
No, not in the chat at least.
Okay. Right. So maybe we should have one more break and then do fold L. I mean, we
Okay.
won't get. Okay,
Yeah.
let's say 10 minutes until 35.
Okay.
Okay.
Okay. Talk to you then. Sorry about that. I forgot to switch on my headset. Can you hear me now?
Yes.
Sorry. I wanted to ask, I know there's like in the assignments, there's something to reverse, whether that has already been done or whether that's still pending. Do you know, Marina or Robertino?
I think it's already been done. Let me double check
Okay.
in case.
Okay, thank you.
Yes.
Okay. So I think when I first introduced reverse in the overview lecture, we did it like with the standard design pattern on list, but then I demonstrated that it's very inefficient. So it's like quadratic complexity. And then there were assignments that showed how to do it efficiently. And this is the solution. So you use an accumulator. That's basically the solution. And so initially the accumulator is the empty list. And then you define a recursive function to reverse. And to reverse the empty list, you just return the accumulator. And to reverse a non-empty list, you cons the head of the list to the accumulator, and then recursively continue with the tail of the list. So maybe just for demonstration, so how does it work if I want to reverse Haskell? So I start, the accumulator is, I start with the empty accumulator, so it's the empty list, and there's the full string. So now in the next step, I cons the age to the accumulator. So there I have just the age, and here I have Haskell. So then I would cons the first element here to the accumulator. So I have AH, scale, and again I cons the S to the accumulator, and so on. We really should do a course on Go. Would be far less typing. And almost there. I could type. Okay, almost done. Empty list, and then the first equation of Go is active and says, okay, if I'm done, if the list is empty, I just return the accumulator. So the result is that the last value of the accumulator, which is Haskell reversed, except I made a typo. Sorry. Okay, so that's this algorithm. And it turns out that that is linear. So you can, if you use this with this accumulator, then you can reverse a list in linear time instead of quadratic. So that's also how the prelude reverse function is implemented. Okay, and as a second example, I mean, we saw how to use fold right to add a list of numbers, but how you would normally do it is also use an accumulator. So to add a list of numbers type A, so you start with accumulator 0. So that's like your subtotal in the beginning is 0. And then, okay, if you reach the empty list, you return the accumulator. And if it's the empty list, you add the head of the list to the accumulator and return with the tail. And that is basically how you would normally do it. I mean, envision a list of numbers. You would start with subtotal 0, and then starting from the left, you would add one number after the other to the accumulator until you are through with the list. And then the value of your accumulator is the sum, the total of the list. And that's also, I think, in JavaScript, there's this aggregate function. And I think in one version of it, you also have this accumulator that you can use. So that's a common way to process lists, to aggregate lists. And if you look at these two definitions, then we see again that there's a pattern that, I mean, they somehow have a similar shape, right? In both cases, we define this helper function go that takes an accumulator and the rest of the list we are processing and the result type, and then does things. So one for the empty list case and one for the cons case. Okay, and we try now to basically abstract what these two examples have in common into another higher order function, similar to what we did for fold R. So first we see that we have this accumulator and that we call go with some initial value for the accumulator. So in the case of reverse, the initial value of the accumulator is the empty list. In the case of sum, the initial value of the accumulator is 0. And furthermore, we see that in each step, so in the case of, in this go helper function, in the case of the empty list, we just return the accumulator. This we do in, that we do in both cases. And then we see in the second case, in the cons case, we use the head of the list to modify the accumulator and then call go recursively on the modified accumulator and the tail of the list. So in the reverse example, what we do with the old accumulator is we cons the head to it. And in the sum example, what we do with the old accumulator is we add the x to it. So we can abstract that away. So basically the two, I mean, everything that's framed in red here now is where these two examples differ. So they differ in the initial value of the accumulator and they differ in how we update that. So we can, for those like interesting spots, we write dots. Then we give names to those. So we call the initial value of the accumulator E and the operation we perform on the old value of the accumulator and the head of the list, op. Now, again, as before, this wouldn't compile because now we have this E and the op, and we mention it here. So we give new parameters to our function. We add this op and E. So now we can call, I mean, use the E and the op there. And now we can figure out the types. But if you do that, then you come to this. So R is the result type, A is the type list elements. So the accumulator has the same type as the result type. And this is the initial value for the empty list. And this is the function to update the accumulator. So given the old value of the accumulator and the head of the list, what is the new value of the accumulator? And this thing is called fold L for left fold. And if I go back to my beautiful pictures, so the idea for fold right was this. So basically you start at the right end with the initial value for the empty list and you perform your operation, your given operation for each element going from right to left. And the left fold is exactly the other way around. So you start at the left with the initial value of the accumulator and then you process the list elements one by one going from left to right and update the accumulator in each step. So that's why it's called fold left for left fold. So that's the name, fold L. And here's this what I try to do with the with my pictures as well. I mean with the comments to see the difference. So if you have fold right, this is this function argument. This is the value for the empty list. So fold right, fold left. What's the difference? It's basically the way you do this. So for fold right, you start at the right end with the initial value, and then going from right to left, update with the list elements. And fold left, you start at the left with the empty value, and then process from left to right each list element. So maybe this is the best picture to understand why it's called fold right and fold left. And for example, I mean, for something like plus, for sum, both would work. So we can use fold right plus 0 or fold left plus 0. And in both cases, applied to the list of elements 1, 2, 3, we would get the same result, namely 6. But the computation that actually happens is done differently. For fold right, it would start at the right like this, and for fold left, it would start at the left like this. And of course, because addition is an associative function, we get the same result in this case. But that's not generally true. Right, and now comes an interesting thing. If we, for example, look at addition. So, I mean, first thing, I mean, let's say, I mean, if we had to guess how sum is defined in, or hang on, let me do it like this. Let me first switch on this plus s minus t, I think is good. No, it's s. I always forget. But there's this help. Plus s, okay. Set plus s. Why don't I set? I must say set, I think. Okay, so that's just to get these some benchmarks about time and memory. So let's say I take the sum of the integers from 1 to 10 million. This is now the built-in sum, I think, or do I hide that? No, so that's the sum that's available from the prelude. And we see it's fast, it's like 1/10 of a second for 10 million numbers, and memory is bad somehow. Right, is that normal that it's so bad? I'm a bit confused now. Whether, did I? Okay, fine, it's. Sorry, I just want to see. I'm a bit confused that it takes so much memory. I mean, 880 megabyte is a lot. And it should, in principle, run in constant memory, right? But that is maybe also not reliable. What this, I mean, maybe this is not the total memory. It's like total allocated one or something. Anyway, let me just try this. Fold right plus 0. Okay, this is good. Okay, that definitely takes more. Let's try fold left. Okay, and now let's do sum again. Okay, so that's interesting. And that's sort of what I wanted, more or less. So let's do this again. So if I do fold right, it takes 3.5 seconds and uses, if I'm not mistaken, 3 GB of memory. If I do fold left, it's better, but it still uses 2 seconds and 1 GB of memory. And if I use the sum that the prelude uses, it's less than a second and 880 megabyte, which is, I still don't understand exactly why it's so much, but nevertheless, it's better. So the question is, I mean, what's the difference? Why does fold right take so long? Why is fold L better? And why is fold L not as good as it should be? Okay, so the first question, fold right versus fold left. If we look at this example, In order to do this, I mean, it has to figure out the Z. So before it can do, I mean, before Haskell can do the first addition, the Z plus E, it has to get to the Z. So in our example of 1 to 10 million, the first number it adds is the last one, the 10 million. So it has first evaluate the whole list in memory. So a 10 million integers long list in memory before it can do the first calculation. So that means it will definitely use a lot of memory. And we see this reflected here when we did this fold right. I mean, it was the worst, like 3.3 gigabyte. And that's because it has to like have everything, the whole list in memory. Now for fold left, it's better because it can already, just looking at the first element of the list, the X, it can already do the first addition. So, and then once it has done that, in principle, it can forget about the X, and so it can garbage collect the X, we should think. That's why fold left in this situation is better than fold right. It, in principle, doesn't need the whole list in memory. Okay, but why is it still so bad and needs gigabytes of memory? Even though in principle, we should naively think as soon as the X is added to the accumulator, it can forget about the X. Then it evaluates the next element of the list, the Y, and so on. So in principle, that should run in constant memory, be fast, because it always only needs the next element of the list in memory to add it to the accumulator. Okay, but it's still like that. Better than fold right, but not good. And the reason is that this is one of the cases where laziness bites us and is bad for us. Because of laziness, Haskell never evaluates anything until it's needed. So these things here, it doesn't need whether it actually has to do the addition. It could be that in the end, we don't care about the sum. In our example, we want to print it on the screen, so we do care. But at this point, Haskell doesn't know that. So it will not evaluate the addition. And how is laziness actually implemented in the computer? It uses so-called funcs. That's basically, you can think of it like a pointer to code. So instead of evaluating something immediately and storing the result, it just remembers how to compute the result on demand. So it basically would have like a pointer to some piece of code that can do this calculation, but it doesn't do the calculation. It just remembers how to do it. And only if the result is actually needed, then it will run this code. So that's how laziness is implemented. And normally that's, we have seen examples where laziness is very nice. But in this example, this means that with this fold left, we build larger and larger func. So in the end, we have basically a func that has all these additions. None of them has been performed. And they're like pointers to code for these 10 million additions, like 10 million funcs. And they are almost as bad as, or just as bad as the original list. So again, we have like 10 million of something in memory. Now it's not the list anymore, it's these funcs, but de facto, it's like almost as bad. So that's the problem. And what we would like to do is to tell Haskell to not be lazy in this case. We want it to not be lazy, do the addition immediately. Because as soon as this addition is done, it can forget about the X and garbage collect it and just update the accumulator and then do the next and so on. Everything should be fine and run in constant memory. Right. But until now, there's no way to do this. So there is no way with what we have learned about Haskell so far to force evaluation of something like that. Though I'm not completely sure that's true, actually, but I think it's true. At least it's claimed on the slides. Okay, so there is one important, right, so this is what I just said. There's one important primitive in Haskell that we haven't seen yet, so that I'll show you now, and that's called seq, S-E-Q, and that can be used to actually do force evaluation. So it has this signature. It takes A and a B and returns a B, and semantically, what it does is like const. So if you give it an A and a B, the result of seek will just be B. So it will, I mean, in that sense, it will completely ignore the A. However, what it actually, I mean, it has like a side effect. And the side effect is that if the B is forced, so if somebody wants to see a B, then it will first evaluate the A. So that's why it's called seek. It enforces that the A is evaluated before the B. Right. What does evaluate mean? There is something, I'm not sure whether that's mentioned here. Evaluate doesn't necessarily mean what you think it means. So it doesn't mean completely compute something. It means it brings it to so-called head normal form, which for data types like list means it evaluates to the first constructor. So evaluating a list, for example, doesn't mean to compute the whole list. It just means, I mean, for a list, there are two cases, empty list and cons. So it would only evaluate which of the two cases is it. Is it the empty list or is it cons? But it wouldn't evaluate further. It wouldn't evaluate the head further or the tail, but it would know whether it's the empty list or not. However, for numbers, it's different. For numbers, it really means what you think it means. So if you evaluate an int, then you really have the number, the actual number. So with this now, we can try to improve the situation. And that is then called fold L prime. So that's a naming convention in Haskell that often things where we want to force intermediate results, also like strict versions, they are called strict versions, they get this tick. I mean, that is just a convention. It's just a name. So we can write this here differently. So that was the old definition of fold L. We write this slightly differently. So instead of immediately putting the new accumulator here, we give the new accumulator a name, egg prime, and then put it there. So what we want is we want to, instead of proceeding like this, we want to evaluate this thing first before we do this, right? That was the problem. We built this large thunk instead of doing the additions immediately. So now, equipped with this new knowledge about seek, what we can do is do this. So like it will have exactly the same result as before, because semantically the seek doesn't do anything. It basically just ignores the first argument. So the result, the overall result will still be the same. But like the side effect will be before it basically does the next step, the seek forces it to evaluate the accumulator first, the updated accumulator. And this, nobody really ever uses seek because there is like syntactic sugar that you can do instead. That's the so-called bank pattern. That's another extension you can use in Haskell. I mean, we are almost out of time, so I think I'll just start with it next time. So I'll just briefly complete this now. So then you can, bank pattern means in front of a pattern, you can put this exclamation point, and that is then exactly this. So this is a nicer way to write it. So writing this exclamation point basically means evaluate this thing before you use it. And this is this fold L prime, and that is basically the sum uses why it's better. And there is a rule of thumb to never ever use fold L, always the prime version. There's actually a debate in the Haskell community whether there's ever a situation where fold L is better than fold L prime. And I think one of the people I admire most in the Haskell community, Duncan, who also like wrote most of the Cardano note or was responsible for it. I think he has a blog post somewhere or read his answer where he has an example where fold L is better than fold L prime in one very weird situation. But normally, I mean, you can just forget about fold L. So always use fold L prime. And yeah, so that's the accumulator pattern with fold L prime. And yes, but we are now out of time. So I will just like repeat that at the beginning of the next lecture. But that is an important pattern for these new, I mean, that is actually, I mean, I very rarely use fold R, I must say, but I use fold L prime all the time. I mean, this situation that you aggregate something that you have to basically loop over a list and aggregate some totals or whatever. That is a very common situation. So fold L prime is extremely useful. Okay, so I think I should stop here. I don't know. Ah, yeah, that's good, because that was any end of this chapter. Okay, are there any questions before we stop?
There was one question in the chat that I didn't fully understand. Maybe the author can ask it like live or clarify.
Yes. Can you still hear me?
Yes, some strain.
Because I get this message, you
Because-
lost your,
Yeah.
it says you lost your network connection, but I can still hear you somehow anyway. Okay.
Yeah,
But now I can't see the chat anymore. And
Yeah, so maybe Bratipa, if you want to ask the question.
Yeah, can you hear me?
Yes, I think so.
I was asking the whole L, and it seemed like it looked like you could be able to implement it using the EQ, because at some point when you're trying to do some of the exams,
I'm sorry. I'm not sure, Karina, if you could, but I couldn't catch.
No, only in the beginning, but then I hear some noise in the back, and yeah, we can.
And now,
Yes,
can you hear me? Okay. So I was saying, while we were doing some of the sums on the list using fold L and fold R, somehow sometimes the answers could come the same. So does it mean in a way you could implement using the EQ, because EQ sometimes used to also look if one side is equal to the other side?
Right. Yes, in the case of sum, it does do the same. But if you use other operators that are not associative, it wouldn't return the same value. So if we subtract the values, for left and for right will give you two different answers.
yes, and I think it has nothing to do with eq, with the eq class. I mean, of course, if you have eq, then you could check that if you for plus, you could check that fold left and fold right in that case does the same with eq. But I think apart from that, it's not related to the eq class somehow. Okay. I'm afraid I have to leave now because I have quite an important meeting. I mean, you're free to stay if there are more questions and ask Robertino, or otherwise we can answer your questions either offline or before the next lecture on Friday. But unfortunately, I have to go now. So thank you very much, and talk to you on Friday. Thank you.
Thanks, Lars. Bye.
Thanks.
Okay, anyone else has questions?
Yes, I have a question about the last example. In the last example, we have the let expression that we are evaluating the expression, but in this case we're just evaluating the in which case applies, or the pattern, or we're actually evaluating the number.
Yeah, so the seek function only has a depth of 1. So if you have a thunk inside a thunk, it will only evaluate the first parts. We will go over that in detail in the next, because that was like an introduction, but then there's more to say to it. But yes, it will only do the first. If you're pattern matching, it will only pattern match, and if you do more calculations on top of that, it won't resolve like the whole thing.
Okay.
Just enough. Yes, just one step deep. There are ways to do it like deeper, but in a simple case, it wouldn't evaluate the whole thing.
Okay, okay. Thank you.
You're welcome. Okay, so everyone, thank you for coming. Make sure to do the homework, and we'll see you on Friday.
You, bye.